Okay, so you have gamma, r at the top, tt, tt's at the bottom. What is that? It takes gtt, which is the coefficient of the t square, takes the derivative of it with respect to the r coordinate, and then divides it by twice the metric coefficient of the r. Gamma is gtt prime over minus 2 grr. In other words, you have the dt square and the dr square. It takes the coefficient in front of the dt square, takes a derivative with respect to this coordinate, the r coordinate, and divides that by this metric coefficient. So the question becomes, is there such a construct in Newtonian gravity which would lead us to suspect that in this higher level theory we have something like this? And if one would in fact have such a theory, which of course one does, we would then expect what? We'll expect to see the following. We have a space-time metric, and remember again, this is, I put no special relativity in it, okay? ds squared, we had this function gtt dt squared plus the spatial part. What is this function gtt going to be? Well, we know that gtt prime is a, so what is gtt? We have a equals phi prime, which corresponded to gamma, this is gamma, prime equals phi prime. And we know that in differential geometry, this is that. So we can now relate these two things. In gravity theory, the acceleration is phi prime, which means that the world line curvature is phi prime, which means that we expect that in our higher level theory, the connection will be phi prime. But we know that the connection should be the derivative of a metric coefficient. So that means that our connection is the derivative of phi. We have gtt prime equals phi prime. It's the same thing. Okay, again, the connection in this curved space-time theory, according to differential geometry, would be the derivative of the metric coefficient, in this case the time-warping metric coefficient. And we know from gravity theory that that which corresponds to this connection is the acceleration, and that is in fact the derivative of phi prime. So phi prime is the candidate to be equal to gt prime. If that's the case, then gtt is simply a constant plus some other constant times phi. These two derivatives are the same, and this is simply that. Okay, let me just write it bigger. gtt prime equals phi prime, so gtt is equal to alpha plus beta phi. Right? Which means that we're going to stick it in here. So we have ds squared, the metric of space-time, is equal to alpha plus beta phi, where phi is the gravitational potential, times dt squared plus the spatial part. Where there's no function, this is totally flat in our theory. Because we only have time warping. All we need is time warping to take into account the curvature of the world line, which is the acceleration. Now, this, of course, our intuition tells us that in the absence of any field, this should be 1. Correct? So we're going to have a 1 over here, and when this potential vanishes, it just becomes dt squared. So we expect this. So we've come all this way without special relativity. In an intuitive way, we haven't derived, of course you can't exactly derive these things, and it's all post-hoc. People only thought of any of this only after Einstein came up with general relativity, and only years later when they went down in depth and understood well enough to see that a lot of this is in Newtonian gravity. Most of the stuff that I did here is not standard, right? Some of it comes up from my own thinking and ways of presenting and so on. Some of it is standard. And it's really, really nice how one sees that one can motivate the idea that space-time is curved, there's a connection, there's a Riemann tensor, and underneath it all is a metric, and that in the case of Newtonian gravity, you end up with this.